Okay, we're going to do our first Laplace transform problem, and hopefully what we're doing here is review for you. Uh, so if we look at so here's our first problem, and if you look at the differential equation, it should look extremely familiar. Y double dot plus 6y dot plus 18y. So we know this has its eigenvalues or poles are at -3 plus or -3i. And here we have it equals 9x x of t. X of t is the input. I believe when we did this problem before, I had f of t. There's no magic in the name. So here we have our familiar initial conditions. Y of 0 equals 2. Y dot of 0 is 4. And x of t, the input, is going to be unit steps. We've done this problem before. All right. In the word of Laplace, I need to Laplace transform this equation. All right, so here I got a y double dot. So we've just in the previous lecture, we looked at how do we handle that. Well, that becomes s squared y of s, and now we start looking at the initial conditions where the s drops down until we wipe them all out here. So we have s squared y of s minus sy of 0 minus y dot of 0. Then we have 6 y dot of s. Well, that's just sy of s minus y of 0 plus 18 y of t becomes y of s equals 9. X of t becomes x of s. So, which is yet to be determined, but in general, anything that's when we Laplace transform, we say if something is x of t, it's generically x of s or whatever. All right. So once we get here, the next step is to gather all the terms. All right, so I'm going to have all the y of s terms, s squared plus 6s plus 18, there it is, times y of s. Then I'm going to take all of the initial condition terms and blast them to the other side. So I have y of 0 plus y dot of 0, see, that's right here. And then I have a 6y of 0, that shows up over here, equals 9x of s, so that's right there. So next step is I'd like y of s represents the output. So I'm going to solve for that. So I'm going to take this, here's the characteristic polynomial, I'll divide it through. Okay. Now, the other thing we'll do is I'll actually take these values for the initial conditions, substitute them in. So all the initial conditions amount to 2s plus 16. Now I'll divide that through. All right, so let's see what happens. We actually have some nice structure that's automatically made by Laplace transforms. So I've got a 9 over the characteristic polynomial times x of s. All right, that's the input. This is now the transfer function. Remember, we said we'd like to have something input times system equals sort of output. That's what we have here. So we have the input. This is called the transfer function. The result, since this is driven by the input, this is the Laplace transform. This whole thing is the Laplace transform of the forced response. So when we go to do Laplace transforms, the idea of separating things into the initial condition response and the forced response is automatic. So here was our initial condition stuff divided by the characteristic polynomial. All right, this is caused by initial conditions. This is the initial condition response. And when we go to do this problem, we're going to get the same forced response and initial condition response that we had before. But when you look at it, in a sense, the problem's all kind of already done. Here's the output. We want y of t. Well, here is the transform of it. It's all done for us. Now we just have to do the inverse Laplace transform, but we actually have one thing we need to do. X of s is a generic representation of the input. The input happens to be a step. So we need the Laplace transform of that step input. So let's knock that one off right now. And so we have a unit step input. Okay, we put the function at time equals 0, it jumps up to 1 and stays there, e to the minus st. All right. Integrate from 0 to infinity. If we just treat s as a constant, we come up with the following. Just a generic unknown constant. Now, I will note for this integral not to blow up, you need to have, when you do this right here, e to the minus s, t needs to overwhelm the s. And that will happen as long as the real part of s is greater than 0. Okay, the real part of s is positive, t, then you have this minus here that'll ensure everything doesn't blow up. But when you use Laplace transforms, except for in two very specific conditions, this doesn't even matter. So when you form Laplace transforms, the fact this s can be any complex number, including a negative one, that would make this a positive number and would make this look like it would blow up. We just ignore it, okay? Don't worry about it. So you can kind of just look at it this way. Deal with this as just a arbitrary variable, just leave it and integrate it through, okay? So Laplace transform of unit step input is 1 over s. Just use it. So if I stick this 1 over s into here, I will now have a full expression for the output. All right, so so the next step is we want to start to take these back to time. But I need two more Laplace transform properties to get there. So when we go to do this, I'll note that the Laplace transform of e to the minus at cos bt is equal to this, s plus a on s plus a squared plus b squared. Now, the roots of when you get down to this, we're going to find a is actually the real part of the root, and b was the damped natural frequency, the complex portion. We'll get there in a moment. E to the minus at sine of bt looks slightly different. So here we have, this will be the frequency, and then we have the same bottom again, s plus a quantity squared plus b squared. Given these tools, we can take this back to time. So we'll start with the initial condition response. And the way you do these things, so I'm just looking at this piece here, don't care about anything else. So I have 2s plus 16 on s squared plus, darken these up a bit, 6s plus 18. When you're doing a Laplace transform, always look to this s piece here on top and look to match it first. All right, so that's a 2s. There's no s here, so that doesn't help me. Here I have an s. So if I put a 2s in front of this, so 2s plus 3, now let's look at this, s squared plus 6s plus 18. That becomes, I can break this up. Well, just notice, when we did this before, the root here is minus 3 plus or minus 3i. Here's the real part, here's the imaginary part. So here's that root here just all exposed for us. And the s plus 3 shows up on top. So we have 2 times s plus 3. So if you look at what that does is, using this transform, I multiply it by 2, I have 2s plus 6. I need 16. So if I have 6, I need 10 more to finish this out. Okay, b is 3. So if I multiply b by 10 thirds times 3 gives me 10. So now I have 2s plus 16 on the top. I have matched this thing. All right, so the moment you do that, this is now 2 e to the minus 3t cos bt. You just go from here, boom, back. And this is e to the minus 3t sine 3t times 10 over 3. Boom, we're there. And from the work we've done before, if you can combine factor out the e to the minus 3t, you can combine these into the following, 3.88 e to the minus 3 cos 3t minus 1.03. Same answer. All right. So now we can look at the input. In looking at the input, x of s is 1 over s, so I just stick, there that is right there, times, here is our characteristic polynomial. We need to do a partial fraction expansion, so that would look like a over s, so we take this term, and this thing here will require a bs plus c on top. Hopefully you've seen that in your math, all right? When you do the partial fraction expansion, whatever you have in the bottom, on top you have something of 1 degree less. This is first degree, therefore we have s to the 0 up top, so it's just a 1. This is second degree, you need a bs plus c above it. All right. define the A. Now, you've hopefully done this before. You should know you can kind of multiply everything through and solve and find A, but there's actually a quick trick. And so what I can do is actually take this S, multiply it through over here. Okay, so here I had this. I'll take this S, multiply it through. They can cancel. And then I take the limit as S goes to whatever the root is here. So the root here this is why we often call it a pole. If S equals 0, it's infinity. That's where the pole name comes from. So to zero this out, it's S equals 0. So I take the limit as S goes to 0. These S's cancel. So now I have 9 over 0 plus 18. That's a half. So now I know what A is. BS plus C, you kind of got to do it out by hand. So here I have a 9. If I clear the fractions here, I would have this A, which is a half, times this piece, plus BS plus C times S equals 9. And if we can add in a plus 0S and a 0S squared over here. All right, if I look at the S squared terms, on this side it's a 0. I have a half, and then S, BS. So the S squared is factored out, so I have 1/2 plus B equals 0. Solve for B as a half, minus a half. Likewise, if I do the S term, there is no S term here, so we have 0 equals 1/2 times 6S, that's 3S, plus CS. Factor out the S, we have 0 equals 3 plus C, C equals minus 3. All right. So now we can do the same game. Here we have minus a 1/2 S plus 3. So we have minus 1/2 S in the front. So once again, we start by matching the S. So we use the cosine term, e to the minus AT cos BT. Here's that S. Here's a minus 1/2. So I've now equalized that part. Okay. And now I need a minus 3. Minus times 3. So here I have minus 1/2 times 3. So that's minus 1.5. I need another minus 1.5. So here's the sine term, which has the 3 here. I multiply that by a half. Boom, I got my minus 1.5. So these two combine to be that. Always start in the cosine first. All right? And so that gives me the following. All right? And here's what we've done in the past. We can combine them into a combination of a sine or a combination of cosines. If I choose the cosine version, here's what that would be. We've seen this before. So if we look here, A cosine B, if we call 3t the C part, then I would have minus 1/2 must equal A cosine B. All right, so here's a minus here. So that means A sine B must equal positive a half, because this minus goes with this thing. All right, so A sine B is a half. Okay, if we square these, you get a half squared and a half squared. A squared is 1/4. You therefore take the square root, you get A is 0.707. We can then do a tangent of the sine over the cosine, and that works out to the following. That would be 3 pi over 4, taking you over there. So this is now 0.707 e to the minus 3t cos 3t plus 3 pi and 4. All right, so now we can combine these. Here's that A over S. Okay, here's the rest of the forced response right here. And then here's the initial condition response that we already did. And if you go check, this is the same answer we had before when we did this. So that's kind of neat. This is a very straightforward, you don't have a lot of tedious things to work out as compared to the method of undetermined coefficients. So I find this a lot easier. That's our first problem. We're going to end there, and we'll do some more.